Alright, so I'm gonna go over this mock exam because I don't think we did it in class on Friday. Yeah. Alright, so estimate the mass of 4.50 times 10 to the 22nd molecules of SO3. So when you're converting from molecules to moles to mass, because that's like the middle point connecting those two values, you're going to use Avogadro's number. So to write this out, 3, and then Avogadro's number is like things per mole. So it's 6.02 times 10 to the 23rd things per mole. So you want to divide by that number because you want moles. 1 mole, and it just so happens that this number is 0.0747 moles of SO3. And then the question is asking for mass, so to go from moles to mass, you multiply by the molar mass. So 0.0747 times 1 mole SO3. And in that, calculating the molar mass is just as simple as adding up the molar masses of the individual atoms. So it's going to be 32.07 plus 3 times 15.999. And then this is about 5.98 grams of SO3. And that is D. Okay, how many moles of N2O4 are there in 76.3 grams of that? And going from grams to moles is really easy. You just divide by the molar mass. So we've got 76.3 grams N2O4 times 1 mole N2O4. And again, we just add up the individual molar masses of all the atoms. So this is going to be 14.007 times 2 plus 15.999 times 4. And that's going to be equal to, I gotta do the calculation. .3 divided by that, and that is going to give us 0.829 moles of N2O4, and that's that one right there. Calculate the mass percent composition of lithium in lithium phosphate. So mass percent composition is just going to be grams of whatever you're looking at over grams total for the molecule. So we have 3 lithiums and this phosphate anion. So the weight of lithium is 6.94 grams per mole, and there's 3 of them. So that is equal to 20.82 grams of lithium in 1 molecule of that, or 1 mole of that. And then PO4 is equal to 30.97 plus 15.999 times 4, because there's 4 oxygens and 1 phosphorus. So that's 15.99 times 4 plus 30.97 is equal to 94.966 grams of that. So total is equal to 115.786. And then for mass percent of lithium, it's just grams of lithium over grams total, which is equal to 20.82 over 115.786, and that is equal to 0.179, or 17.9%, which is this one. Okay. So determine the empirical formula for a compound that is 36.86% nitrogen and 63.14% oxygen by mass. Okay, so it's giving us these percentages. So the first thing you do is convert them to grams, like out of 100. So nitrogen has 36.86 grams. Oxygen has 63.14 grams. And then when we're finding the empirical formula, we're gonna convert all of these to moles and divide by the smallest number of moles to get that ratio for the subscripts in the formula. So, So we divide by the molar mass of nitrogen, which is 14.007. Divide by that. The molar mass of oxygen is 15.999. We get 36.86 divided by 14.007. We get 2.631 moles of N, and then we get 3.946 moles of O. Divide everything by the smallest number of moles. With this we get 1, with this we get 1.5. So then we know that we can write this as the subscript of 1 for N, and then for oxygen 1.5, but we want, for the empirical formula, we want whole number subscripts. So you multiply everything by 2, and then you get your empirical formula is N2O3, and then that's D. Okay. Determine the molecular formula for a compound that has a molar mass of 114.23 grams per mole and an empirical formula of C4H9. So when we're finding the molecular formula, what we do is we ratio the molar mass of the actual compound over the molar mass of the empirical compound. So we're given the molar mass of the molecular compound, I guess, the thing we're trying to find, but we don't have the molar mass of this. So to get the molar mass, just add up the individual masses of all the atoms. So then that's 4 times 12.011 plus 9 times 1.008 plus 9 times 1.008. And then we get the molar mass of this empirical formula is around 57.116 grams per mole. And then we ratio them, so we put this over this, so 114.23 grams per mole over 57.116 grams per mole. And that's about, I mean, you guys can already tell it's probably going to be around 2. And it's, yes, 1.999, which is approximately 2. So what this number 2 gives us is you want to multiply all of the subscripts in the empirical formula by 2 to get the molecular formula. So multiplying this again, everything by 2, you get C8 or H18, and that is A. Okay, so which one of the following samples contains the largest number of molecules? Okay, so what we want to do here is we want to find how many moles are in each of these things, and you know that for a mole of any substance it has the same number of molecules, so you know that right at the start these have the same number of molecules. And then for these two, you just want to convert those to moles and see which one has the highest number of moles, because highest number of moles means highest number of molecules. So 160 grams of, is that methane, CH4, divided by the molar mass of 12.011 plus 4.032, which is just 4 times the mass of hydrogen. Okay, and then dividing that. We get around 9.97 moles of CH4 for C, and then doing answer choice D, 160 grams of C3H8 times 1 mole. And again, when you're trying to go from grams to moles, you just divide by the molar mass of that compound. So the molar mass of this is going to be 36.033 plus 8.064, which I just did that by multiplying the 3 and the 8 by the masses of carbon and hydrogen. 0.064, 160 divided by that number, 44.07, you get around 3.628 moles of C3H8. And again, like we said, these two right here are the same number of molecules, because Avogadro's number and the relationship with moles has no correspondence to what the actual species is. It's just a thing. So 3 moles of anything is the same amount of molecules. And then this is slightly more at 3.628, but this is way bigger at 9.97 moles of CH4, so your answer is C. All right, how many H atoms are there in 5 moles of methane CH4? This one's pretty easy, but you want to make sure you look at what it's asking for. It's asking for hydrogen atoms, not just how many molecules there are of methane. And you want to notice that there's 5 moles of CH4, and then for every 1 mole of CH4, there are 4 moles of hydrogen, right? Because there's that 4 subscript. And then to get from moles to atoms or things, you want to multiply by Avogadro's number times 10 to the 23rd. For every 1 mole of hydrogen, everything cancels. And then you're going to get 1.20 times 10 to the 25th H atoms. And then that is answer C. All right, how many grams of oxygen are formed when 6.21 moles of H2O react? So this is again using a mole ratio, pretty similar to the last problem. Okay, so you want to notice that for every 2 moles of water that react, only 1 mole of oxygen is actually formed. So start with our given. Always start with your given in stoichiometry. 6.21 moles of H2O. And then you want to use that internal mole ratio of 1 mole O2 per 2 moles of H2O, right? Because we looked at that. Okay, and that makes sense because we want to cancel this out and we want to be left with just moles of O2 to transfer to grams. And that is going to be just half of that, so 3.105 moles of O2. And then again, to go from moles to grams, you just multiply by molar mass. One mole of O2 is 31.998 grams of O2. Those cancel. Then we get 3.105 times the 31.998. Okay, so I put that on my calculator wrong. So the answer is 99.353 grams of O2, and that is pretty much close to only that answer. Okay. Consider the following balance reaction. How many grams of water are required to form 75.9 grams of nitric acid? Assume there's excess NO2 present. The molar masses are as follows. Water is 18.02. Nitric acid is 63.02. Okay, so we want grams of water. And this is kind of our given. I know it's weird to work backwards with our given, but if we know how much nitric acid was formed, then we can backtrack that to see how much water was actually used to form that. So first thing you want to do when you're doing stoichiometry is always convert everything to moles. So 75.9 grams of nitric acid. And then when converting to moles, we know this, divide by molar mass. 1 mole of nitric acid, and the molar mass is 63.02 grams, which is 75.9 divided by 63.02 is 1.204 moles of nitric acid. Okay, and then just like the last problem, we'll look at the mole ratios. For every 2 moles of HNO3 that react, 1 mole of, or for every 2 moles of nitric acid that were formed, 1 mole of water was used. So we set up this 1.204 moles of HNO3, and we want to get rid of this HNO3 here. So we put the 2 moles HNO3 from the mole ratio in there to 1 mole of H2O, and then for every 1 mole of H2O, it is 18.02 grams H2O. And that is equal to, divided by 2 times 18.02 is about 10.9 grams of H2O. Given the theoretical yield in moles of CO2 from the reaction of 4 moles of C8H18 with 4 moles of O2, or give the theoretical yield, not given. Okay, so the theoretical yield is going to be the calculation from whichever one of these 4 moles of either that gives us the most amount of product, which is CO2 in this case. So let's start with the C8H18, which I think is octane. All right, what in the world? 4 moles of C8H18, and again we're going to use that internal mole ratio. So for every 2 moles of this that react, 16 moles of this are produced. So we want to get rid of this right here. So we put this on the bottom, and we want moles of CO2, which is 32 moles CO2. So that's how much 4 moles of this will give you. Now we're going to try this. 4.00 moles of C8H18. Set this up exactly the same like we had it, but for this mole ratio, we're going to be using this and this. So that was my mistake. 4 moles of O2. And then in the internal mole ratio, there are 25 moles of O2 that react for every 16 moles of CO2 produced, and that is around 2.56 moles of CO2. And our answer is C. And I think I made a mistake with the theoretical yield explanation earlier. So this is just how much we could make with these theoretically, like if everything reacted and everything went into the forward process. So yeah, it's not just whichever one creates the most. Because even if you had these, you could only make at most 2.56 moles. This one right here. Okay. Determine the theoretical yield of hydrochloric acid. 40 grams of BCl3 and 38.5 grams of H2O reacted according to the following balanced equation. This is just like the last problem. We're going to do stoichiometry to convert to grams of 2 grams of HCl and just see which one, or just see how much we can actually make. Okay, so let's start off with the BCl3. So 40 grams of BCl3. And again, when we're doing stoichiometry, we want to convert everything to moles first to get from grams to moles multiplied by the molar, or divide by molar mass. And the molar mass is 117.16 grams. And then using this internal mole ratio of 1 mole reacts for this, 3 moles are created. So we want to get rid of the BCl3. So 1 mole BCl3 for every 3 moles HCl. And then for every 1 mole of HCl, 36.46 grams, I guess, exist. And that number is 40 times 3 times 36.46 divided by 117.16 is about 37.3 grams HCl. And then we just do the same thing for the other reactant of water. So we start with 38.5 grams of water and then convert that to moles so we can use the internal mole ratio, and then when we look at the internal mole ratio again, for every 3 moles of water that react, 3 moles of HCl are formed. So that's basically like a 1-to-1 ratio. So we don't really have to write the 3's. It's 1 mole H2O for 1 mole HCl, and then again multiply by the molar mass to get weight, or I guess grams. And that's going to be 38.5 times 36.49 divided by 18.015, which is about 77.9 grams HCl. And if given both of these, 40 grams of BCl3 and 38.5 grams of H2O, you can only, or I guess the amount that you can make with the BCl is 37.3. No matter how much you have of water, that means you can only make this amount. So then the answer is going to be D. That's the theoretical yield. Oops. So determine the percent yield for a reaction that produces 28.65 grams of iron and 50 grams of iron oxide with excess aluminum, or react with excess aluminum according to the following reaction. So we know that percent yield is equal to actual over theoretical times 100. Okay, so we know that this is the actual, and we just need to find the theoretical, which is just following through with stoichiometry from amount of reactant to amount of product, and that'll give us the amount that we would theoretically create in product if everything was perfect and every reactant was used up in its entirety. So we're going to start with our given, which is 50 grams of iron 3 oxide. So And always when we're doing stoichiometry, we always want to convert to moles, and we do that by dividing by the molar mass. So the molar mass of iron 3 oxide is going to be 55.85 times 2 plus 15.999 times 3, and that's per 1 mole, and that is going to give us about 0.313 moles of iron 2 oxide. And then we're going to continue on with what we just got. And then again, we're going to have to use that internal mole ratio. It's never going away, so you should get used to it. For every 1 mole of this that reacts, we create 2 moles of iron. And we want to get rid of this, so we put this 1 mole that reacts of iron 3 oxide in the bottom. And we want this iron that we create, so 2 moles of Fe. And then for every 1 mole of that, there exists 55.85 grams of iron, which is equal to times 2, which is equal to 34.97 grams of iron theoretical, because that's how much we would get if everything was perfect, but it's not. So then when we're doing percent yield, we get the actual, which is this, the 28.65 divided by 34.97, our theoretical, times 100. And then we get about 81.92%, or this. I guess I did some rounding differences, but yeah. How many moles of whatever that is are contained in 548 milliliters of a 0.0788 molar, whatever that is, solution? So this one's pretty easy. You just kind of remember the molarity equation, which is moles over liters of solution. And then rearranging this, doing algebra, multiplying everything by L, that cancels. You get N is equal to liters times molarity, which is equal to 548. And remember, this is liters, not milliliters, so you're going to have to convert that, divide by 1,000. So that's going to be 0.45548 times the molarity of 0.0788 is equal to around 0.04318, which is basically, since they're doing in scientific notation, 4.32 times 10 to the negative second moles, which is your answer choice A. Okay, assume that you have 700 milliliters of a 2.5 molarity sodium chloride solution in a beaker. If you evaporate all the water, how many grams of NaCl do you expect to find in the beaker? Okay, so this one's pretty simple as well. I think it's kind of the same setup. So you have molarity is equal to moles of solute over liters of solution, which implies that moles of solute is equal to molarity times volume, liters, which is equal to 2.500 times 0.700. Remember to convert those milliliters to liters because molarity is in terms of liters. So when you get 2.5 times 0.7, you get 1.75 moles of NaCl. And then it's asking for how many moles there are, or how many grams there are, so just multiply by the molar mass, pretty simple. For every 1 mole of NaCl, there are 58.44 grams of it. And then that's going to be equal to about 102.27 grams NaCl, which is answer choice B. Which of the following aqueous solutions will conduct electricity most efficiently? So this is just looking at electrolytes, and strong electrolytes are ionic compounds because they will dissociate 100%. So we can automatically tell that this one is off the charts because that's not an ionic compound, but these three are. And then if all three are ionic compounds, you want to see which one has the most ions after it's dissociated, because the larger number of ions, the more that electricity can conduct. So if you see that in this first one, the 0.15 molarity HCl, when this dissociates, it'll dissociate into H plus and Cl minus ions. And if the molarity is 0.15 molarity, that's 0.15 moles of this for every liter. You know there's going to be double the amount of solute concentration, because there'll be 0.5 moles of H plus and 0.15 moles of Cl minus. So that's going to be total of 0.3 molarity of solute. Okay, so that's our first contender. And then we see the same thing basically for answer choice B. 0.15 molarity, whenever it dissociates, it'll dissociate into Na plus and Cl minus. And if the total concentration of the actual compound is 0.15, whenever it dissociates into Na plus and Cl minus, it'll have 0.15 molarity Na plus and 0.15 molarity Cl minus, so that's a total of 0.3 molarity of solute. And then we look at C, and then we have that will dissociate into K plus and Br minus. And if the molarity of the total compound before it dissociates is 0.4, we know that it'll dissociate into two pieces. So instead of 0.4 moles per liter of that, it'll have twice that because it'll dissociate into two pieces. So then that total molarity at the very end, after all that dissociates, will be 0.8 molarity of solute, which is way bigger than these two. So yeah, the most amount of solute concentration will conduct the electricity most efficiently. So we know it's KBr, so it's choice C. Which of the following metal cations would form an insoluble phosphate salt? Okay, so this one's pretty easy as well. We know that from our solubility rules, all group 1 metals and the ammonium ion are always going to be soluble no matter what. This is group 1, this is group 1, this is always soluble, and this is group 1. So you know none of these are going to be insoluble. So what is the concentration of nitrate ions in a 0.125 molarity magnesium nitrate solution? So we know molarity is moles per liter. So I guess we don't even really need that. So you see that for every liter of water, there's going to be 0.125 moles of this. And then whenever that dissociates, because this is an ionic compound, that'll dissociate into Mg2 plus and 2 of the NO3 minus nitrate ions. So we know that if the overall concentration for this compound is 0.125, when this dissociates into all of its ions in it, when it dissociates into all of its ions, it'll have 3 times this concentration right here, which is 0.375, but we're only considering the nitrate ions. So this 2 right here means that you're going to double this concentration for the overall solution, and then you can get the concentration of nitrate ions, which then that is just going to be answer choice D, 0.250. Balance the chemical equation below. What is the coefficient in front of water? Okay, so when you're balancing these chemical equations, I'd always leave oxygen last because that's just annoying to deal with. And look for the things that only appear in one substance. So this is how I would do it. So there's only nitrogen in this compound and this compound. All right, there's only nitrogen in these 2 compounds, so we know those are fine right now, being 1. We can just put those there as placeholders. And then go to oxygen. Not oxygen, hydrogen. There's 2 here, but then there's 3 here. So what that means is that you have to find their what is it, least common denominator or whatever it is. So then you're gonna multiply this by 3 and this by 3. All right, let's redo that. Multiply this by 2 and this by 3, so that you'll get 6 hydrogen and 6 hydrogen on both sides. So then you can put a 3 here, and then we can replace this with a 2, and we can still see if everything matches up. We have 2 nitrogens, 3 nitrogens. That doesn't add up anymore. So then you can replace this with a 2. So then now we have 2 nitrogens on both sides. We have 6 hydrogens on both sides. And then we've got, on the right, we've got 2 oxygens from the nitrogen monoxide, and then 3 from the water. So that has a total of 5 oxygens. So we can do this. We can do 2.5. 2.5 times 2 is going to be 5 oxygens to balance that out, but then that doesn't work because you want, whole number ratios or whole number coefficients. So then we can just multiply everything by 2 and it'll still be the same ratios. So then that'll be 4, 5, 4, and 6. 4, 5, 4, and 6, and the coefficient in front of water is 6, so it's E. Determine the concentration of a solution prepared by diluting 25 milliliters of a stock 0.118 molarity calcium nitrate solution to 150 milliliters. Okay, so this is the M1 V1 is equal to M2 V2. All right. So we know that this M1, the very first one, we know that the stock is 0.118 molarity, and we also know the volume of that, which is 0.25 or 25 milliliters. And then we also know the second volume, this right here, is to be this. So what we're looking for is this right here. So then you can do algebra and move everything around so that M2 is equal to M1 V1 over V2. And for this, normally you want to do molarity concentration or molarity calculations in liters, but since you have milliliters over milliliters, it'll cancel out and it doesn't really matter. So then you can plug both in, and you'll still get the same concentration and it'll be correct. So then M1 is 0.188. Volume 1 is this right here from the stock solution, 25 over the second volume of 150. And that's going to be equal to 0.188 times 25 divided by 150 is about 0.313 molarity, which is answer choice C. Alright, so what are the spectator ions in the following reaction? And this is just an acid-base neutralization. And we know that for acid-base neutralizations, the overall net reaction, the thing that's actually occurring, is H plus OH minus creates H2O in the liquid form. And I noticed a mistake. There's not supposed to be a 3 there, so don't worry about that. So we already have this molecular equation. I don't know why I'm circling that. So now we should start by trying to write the ionic equation so we can figure out what the spectator ions are, which aren't in the reaction. So then we start with 3H plus AQ plus this phosphate anion, also AQ. Always remember to write your states. I don't know why. Just do it. I'm just kidding. It's important. Plus 3 Na plus AQ plus 3 OH minus AQ creates 3 Na plus AQ plus another phosphate anion plus 3 H2O. And then we're just going to try to find the things that appear on both sides in the same states, because that means that they're not really taking part in the reaction at all. So first we notice that this PO, this phosphate, is on both sides. It's in the same state on the left and right, so it doesn't matter. Same thing with this Na plus. So then your overall reaction is 3H plus 3OH minus creates 3H2O liquid, which those are all 3, so it doesn't really matter. So then now we have H plus OH minus creates H2O. Look at me forgetting to put on my solid states, or my physical states. Okay. So if that's the overall reaction, we look at the things that canceled out to find the spectator ions, and that's just going to be this phosphate and this sodium. So then that is answer choice A. Write a balanced equation to show the reaction of sulfurous acid with lithium hydroxide to form water and lithium sulfite. Okay, so I don't know if you guys went over this, but so the anion sulfate is SO4 2 minus, and the anion sulfite is SO3 2 minus, and the name of this acid, H2SO4, is sulfuric acid, and then the name of this acid, SO3, is the same thing as sulfuric acid, but just replace the IC with an OUS, and that's sulfurous acid. But then under the equation, we have H2SO3 AQ plus LiOH. No subscripts there because both positive or negative one charge, creates H2O plus lithium sulfite, which is Li2SO3, right? Because there's a positive charge there, or negative 2 charge there, and only positive 1 on lithium. So you need 2 lithiums to make that a neutral molecule. Okay. So let's look at this. Let's look. Okay, so I'm going to start with the lithiums because there's already one thing I can fix there. All right, so there's 2 lithiums on the right side, but only 1 on the left side. So I'm going to multiply this by 2, and let's see what that does. So we have 2 lithiums on both sides, and then 4 oxygens on the left side, and then that leaves only 2, I'm in hydrogens, 4 hydrogens on the left side, and that only leaves 2 hydrogens on the right. So then we multiply this by 2. So that's the same number of lithiums on both sides, the same number of hydrogens on both sides, and also the same number of sulfites on both sides. And then we look at, oh yeah, we're good. Because we also have 2 oxygens, the lone oxygens that aren't in the polyatomic ions. So then it's just 1, 2, 2, 1 for the coefficients, which is answer choice B. Cool. give the net ionic equation for the reaction, if any, that occurs when aqueous solutions K2S and iron nitrate are mixed. Okay, so I'm going to start with K2S plus Fe NO3 2. It's going to create, and this is where we look at our solubility rules and we kind of match up the other things. We already know that these are going to dissolve in water because potassium is a group 1 metal that's always soluble, and this nitrate is always soluble. So we know those are both aqueous, and we know those aren't going to form to create any insoluble compounds. So then we look at opposing anion and cation combinations. So this will create FeK2 plus, that was way wrong, holy crap, KNO3 plus FeS, and then this is always soluble because it's got a group 1 and a nitrate, so we know that's good. That's going to be aqueous. And this is an iron sulfide, and we know that sulfides are always going to be insoluble. I think there's a couple rules, but if it's an iron sulfide, let me just look at it. It looks insoluble. So then we know that the atoms in the reaction are going to be Fe2 plus S2 plus creates FeS. And we want the net ionic equation, so that is going to be FeS. Answer choice D. I hope that's right. All right. According to the following reaction, how many moles of lead chlorite are formed when 420 milliliters of 0.550 molar potassium chloride react with excess whatever? Okay. So we want moles of this, and we're given this and this, and you should automatically see this. There should be like a bell ringing in your mind that molarity is equal to moles over liters. Changing that around, you get moles equal to molarity times liters, and you're given both molarity and the volume, or the liters of the KCl solution. So you just plug those in. Remember to convert the milliliters to liters. 0.420 times 0.550 molarity is equal to 0.231 moles of KCl, and this is just straight stoichiometry using the mole ratios and everything like that again. So start with the new given we just got, the 0.231 moles of KCl, and for every 2 moles of KCl that react, we produce 1 mole of PbCl2. We want to get rid of this, so we put this on the bottom. 2 moles of KCl react to produce 1 mole of PbCl2, which is just going to be half that, which is around 0.1155 moles PbCl2, and that is answer choice D. Okay, all right. Made a mistake on that. So, determine the oxidation state of P in this phosphide anion. So we know that the oxidation number total must equal the charge for an ion. So we know that the oxidation number total, when everything is added up, has to equal to this -3. We know that oxygen is always -2, and there are 3 of them, so total for oxygen is -6. And then what do you add to -6 to get you to -3? This phosphorus is going to be a +3, not a -3. Cool. And then what element is reduced, if any, in the following reaction? You can just look at this. This is obviously a redox reaction. Because look at this. We have 0 for this because it's a pure element. And then the overall charge on this, you guys remember how the charge on the ion has to equal the oxidation number total. And we know that this NO3 is a nitrite anion, which has a charge of -1 total. So we see this is -2 always for oxygen, and there's 3 of them, so it's -6, so nitrogen is going to be +5. And this is going to be a +1 to make that a neutral thing. And then we see silver on this side has a 0, and then look over here, this also has a -1 total charge. This has pretty much the same thing, -2 for each oxygen, but there's 3 of them, so it's -6 total. And then a +5 to make that equal this -1 charge, and then this is going to be a +1. So we know that Zn went from 0 to +1, and then Ag went from +1 to 0. And then we know that from oil rig, our awesome mnemonic, reduction is gain, and that means reduction is gain of electrons. And gain of electrons is a little counterintuitive because you would think that your number goes higher, but electrons are negatively charged, so that means it's going to go more negative. And we know the one that did that was the silver. It went from +1 to 0, so it went more negative. And then that's answer choice D. Oops. Yeah, cool. I hope that helped.